Tonight, the debate on immigration reform. Two of the world's most acclaimed academics will explain their statistical analysis on the subject of immigration. Tonight, we will explore this claim in depth as we examine the underlying question: is there a significant relationship between provincial crime rates and provincial immigrant population? With us today to develop an understanding of this question are two statistical experts, Dr. Brittany Drury, political analyst with the University of Cambridge, and Dr. Emma Perrin, statistics and math professor at Harvard University. Dr. Perrin, Dr. Drury, welcome and thank you for being with us this morning.
Thank you for having us.
Pleasure to be here.
Dr. Drury, today we'll be taking the chi-square approach to answering this question. Could you please explain a little of what the chi-square is and why we're using it in regards to this question?
Happily. The chi-square is a method of statistical proof used when there is no assumptions for the shape of the curve and the statistics being compared are nominal. The chi-square is ideal for the question at hand because of its ability to determine the independence of variables from one another. The statistics being utilized, being crime rates and provincial immigration numbers, can be converted into nominal statistics, which is ideal for the chi-square.
Dr. Drury, could you please walk us through the numbers you will be using?
To begin to test our hypothesis through using chi-square regarding the relationship between immigration and crime rates within British Columbia and Ontario, we must first create a bivariate table. Bivariate tables are called so because they display the scores of cases on two different variables at the same time. The horizontal dimension is referred to in terms as rows and the vertical dimension as columns. Each column or row represents a score on a variable, and the intersection of the row and columns, known as cells, represent the various combined scores on both variables. Lastly, the sums of each column and row are referred to as marginals. This terminology will come into play with the introduction of later formulas. The construction of our table, comparing crime rates and immigration rates in both British Columbia and Ontario, will look something like this. With immigration and crime running along the first vertical axis and the provinces in question along the top horizontally, our obtained information is laid out in an organized manner with the column and row marginals clearly identified. As with all methods of hypothesis testing, we will be employing the five-step model for organizing our data. To begin, step 1, making assumptions and meeting test requirements. Within the case of chi-square, we are not required to make any assumptions regarding the shape of the sampling distribution. However, we must state two things here. First, we must state the model of our sampling frame, which is and always will be independent random sampling. As the chi-square test is founded upon independence between variables, the samples must always be simple and random. Secondly, we must state the level of measurement which we employed, in this case being nominal. Step 2. Stating the null hypothesis. Ultimately, the chi-square test tests for independence. The concept of independence refers to the relationship between the variables, not the samples. Two variables are independent if the classification of a case into a particular category of one variable has no effect on the probability that the case will fall into any particular category of the second variable. In other words, the variables would be independent if crime rate and immigration rate were completely unrelated to each other. The null hypothesis in the case of chi-square states that the two variables are independent. If the null is true, the differences between the observed, symbolized as f sub o, and the expected frequencies, symbolized as f sub e, will be small. The null hypothesis is false, however, if there should be large differences between the two. The greater the differences between the expected and observed frequencies, the less likely that the variables are independent and the more likely that we will be able to reject the null hypothesis. As usual, the research hypothesis directly contradicts the null. In the case of our experiment, the null and research hypothesis are as follows. H null, the two variables are independent. Provincial crime rates are not related to immigrant populations. H1, the two variables are dependent. Provincial crime rates are directly related to total provincial immigrant populations. Step 3. Selecting the sampling distribution and establishing the critical region. The sampling distribution of sample chi-squares, unlike the Z and T distributions, is positively skewed with higher values of sample chi-squares in the upper tail of the distribution. As with all tests of hypothesis, with chi-square we compute a test statistic, x squared obtained, from the sample data and then place that value on the sampling distribution of all possible sample outcomes. Specifically, the x squared obtained will be compared with the value of x squared critical that will be determined by the values given in Appendix C. This table is similar to the T table with alpha levels arrayed across the top and degrees of freedom down the side. Degrees of freedom are the number of values in a distribution that are free to vary for any particular statistic. The values associated with degrees of freedom are calculated through the formula df equals r minus 1 times c minus 1, where r represents rows and c columns. A table with 2 rows and 2 columns has 1 degree of freedom as 2 minus 1 times 2 minus 1 equals 1. Similarly, a table with 3 rows and 2 columns has 2 degrees of freedom as 3 minus 1 times 2 minus 1 equals 2. In the case of our experiment, our table has 4 rows by 2 columns, leaving the formula as 4 minus 1 times 2 minus 1, giving us a degree of freedom of 3. Setting alpha at 0.05, we then consult Appendix C, where 0.5 alpha and a degree of freedom of 3 intersect, results in an x squared critical of 7.815, represented as such. Step 4. Computing the test statistic. This is where things start to get confusing, so listen up. In the fourth step of this test, we are focused on computing the value of x squared obtained through the formula, the sum of frequencies obtained minus frequencies squared divided by frequencies expected, where f sub 0 is the cell frequencies observed in the bivariate table, and f sub e is the cell frequencies that would be expected if the variables were independent. First, in our search to define x squared obtained, we need to calculate the values of f sub e, the expected frequencies. Here we must work on a cell-by-cell basis, calculating the expected frequencies of each cell using the formula f sub e equals row marginal times column marginal divided by n. That is, the expected frequency for any cell is equal to the row marginal times the column marginal divided by the total number of cases in the table depicted as n. Using our case as an example, multiplying the total row marginal of immigration rates, 0.01, by the total column marginal for Ontario, being 4,016.07, divided by the total number of cases, being 11,743.01, gives us a cell expected frequency of 0.038, independent to that particular cell, as shown here. As another example, we took the total rate of violent crimes occurring in both Ontario and British Columbia and added them together to get a row marginal of 2,283. Then, following the formula, we multiplied the row marginal by the column marginal of Ontario to get 9,168,687.81, which we then divided by n equal to 11,743.01, resulting in an f sub e of 780.77. After completing our calculations for each cell, we then constructed a new second bivariate table labeled F sub E, housing the expected values of each variable as based on our previous calculations. Note that the totals for the columns and rows in both charts, F sub O and F sub E, are exactly the same. This will always be the case, and if the totals do not match, you have probably made a mistake in the calculations of the expected frequencies. Almost done, just a few more calculations to go. As our last step in calculating, we must now use our formula for x squared obtained. The sum of frequencies obtained minus the sum of frequencies expected squared divided by frequencies expected. Now that we have calculated our values for FE and have our values for FO, we can, as Alway would say, just plug and play. The easiest way to approach this formula is the construction of a third and final table, constructed with the use of 5 columns. As you can see, the columns are labeled as differing stages in the calculation process. First, by listing all of the values for F sub O and F sub E, we can clearly see the numbers in an orderly fashion. Then, moving to the third column, we subtract each F obtained value from its corresponding expected value, then continuing to square it in the fourth column. To end our calculations, we then divide our squared values by the corresponding expected value to get our final value for that cell. As an example, take into consideration our second case listed in row 2. Beginning with an F obtained of 901 and an F expected of 780.77, we then subtract 901 from 780.77 to get 120.23. 1 squared is equal to 14,455.25. Finally, we can divide our squared value of 14,455.25 by the expected frequency of 780.77, giving us a final value of 18.51. As you can see, we continued to do this for each value until our chart was complete. Now for the final step, we will address completing the sum of portion of the formula. Through adding together all of the values in the fifth and final column of the table, we are able to identify our x squared obtained, in this case being 182.09. Step 5. Making decisions and interpreting the results. In this step, we are comparing the test statistic with the critical region. Our x squared obtained was determined to be 182.09, where our x squared critical was found to be 7.815. As the obtained value is larger than that of the critical, we can see that the test statistic falls into the critical region, and therefore we can reject the null hypothesis of independence. In the case of our results, this leads us to concur that our research hypothesis was correct in stating that crime rates and immigration are in fact related, and there is a significant relationship between the two variables.
Interesting. So you're saying that by working through this problem, we can see that?
Precisely.
Dr. Perrin, you have another way of working through the numbers.
By using SPSS and the 2006 shortened survey database available through Nelson Education, it is possible to construct an answer through the computer program. Unfortunately, we cannot work with immigration numbers and crime rates as Ms. Drury did, as they are not present on the system. However, by instead using the two nominal statistics of citizenship and low income before tax status, we can use the statistics available to give the viewers at home a chance to see how the SPSS system utilizes the chi-square.
For those of us who don't really understand and we're not familiar with this, could you please talk through the SPSS system?
I'd be happy to. Now that we've established our variables of citizenship and low income before tax status and created a null hypothesis, we can start working the data through SPSS. To start, we look to the main menu bar, where we choose Analyze, then across to Descriptive Statistics, and finally Crosstabs. Once we've chosen Crosstabs, we will highlight our first choice, Citizenship, and use the arrow bar to move the variable into the rows box. Similarly, we will highlight our second variable, low income before tax status, and use the arrow bar to move it into the columns box. Next, we will click on Statistics at the top of the window and move to select the empty box next to chi-square. Once that has been done, select Continue, which will take us back to the crosstab screen. Next, we will select the Cells button located underneath Statistics, and this will take us to the cell display. Once there, we click the empty box next to Expected in the Counts box, and then Column in the Percentages box. By doing so, SPSS will generate expected frequencies and column percentages for the table. If we now select Continue and then OK, we can produce our final output and proceed to examine the numbers.
So we can see that SPSS has generated 3 different charts. Dr. Perrin, could you take a moment to explain what exactly our viewers are looking at?
Of course. I'd like to turn your attention to the cross-tabulations table first. This table is a relatively straightforward 2x2 table. We see variations of the categories of citizenship establishing our row. The numbers following horizontally from the word count indicate the number of citizenship cases by category which qualify for the specific economic category. This is also demonstrated in the same fashion through a breakdown of percentages. For example, we can see that 179 people who are Canadian by naturalization qualify as non-low income, which accounts for approximately 14% of the total number of non-low income sampled individuals. The count is notable in other aspects as well. The count represents observed frequencies, and by placing the numbers in contrast with the expected count numbers, we are able to conclude the likelihood of variables being independent. As Dr. Drury explained, we are observing the differences between the observed frequencies and the expected frequencies, because the greater the difference between these numbers, the less likely that they are independent. If the numbers prove to be independent, then we can reject our null hypothesis, and we're one step closer to discovering the relationship between our variables.
Will we need to compute that information by hand, as Dr. Drury previously demonstrated?
No, thankfully SPSS has an answer for almost everything. In the chart following the cross-tabulation table, we have the chi-square test. And in this table, SPSS eliminates the need for statisticians to use the distribution of the chi-square table to compare the value of the chi-square obtained against the value of the chi-square critical. To clarify, when I speak of the chi-square obtained in this table, I'm referencing what SPSS has labeled the Pearson chi-square number, and the degrees of freedom are beside the values in the third column and labeled as DF. Without having to use the chi-square table located in the back of the Nelson and Healy textbook to conclude the exact probability of obtaining this exact pattern of cell frequencies by random chance alone, we can instead easily observe the decimals under the exact significance column, which is labeled here as assumption significance two-sided on our table. In this case, we can see that the exact significance is 0.000. This number is below alpha equaling 0.05, which is the standard indicator of a significant result in the social sciences. Thus, our chi-square analysis enables us to reject our null hypothesis. This rejection inversely concludes that there is a significant relationship between the citizenship status of a Canadian resident and their low income before tax status.
That's enlightening. Perhaps further research will demonstrate the relationship between the increased likelihood of citizenship affecting low income and the relationship between immigration and crime levels. Dr. Drury, Dr. Perrin, thank you both very much for your insight on these issues and for your masterful use of the chi-square. I'm sure viewers can't wait to attempt their own chi-square at home. Thank you for watching, and goodbye.
Thank you for having us.
Thanks again for having me.